Hello everyone, welcome back. Today, we're going to learn about the fundamental theorem of calculus. So our goal is then to understand it and also be able to use it to help us find the values of integrals. So as you imagine, it's called some of the fundamental theorem of calculus means it's really important, and it is. And basically, this is how it finally show how we connect derivatives to integrals. All right, so remember, an integral, of course, a derivative gives us the instantaneous rate of change of something. And then an integral basically gives us, then for some function, basically, if we add up all those little changes, then that gives us like a total accumulation, total sum of everything. They kind of adds everything together. Okay. So you can think of it as if your water is pouring water into a bucket, the rate at which water goes into the bucket at any moment, to think of that as your derivative. And then if you add up, all the water that goes in the bucket, all the different instances, even if it's moving at different speeds or different amounts at different times, all that addition, all the accumulation of water, that gives you the integral over some amount of time. Okay, so let's introduce this fundamental theorem of calculus. So what it says, first we can start off with something called an area function. So first, kind of the usual thing, we say if a function f is continuous at some interval from a to b, then we're going to find what's called an area function like this. So the area function is just the integral from a, the start of our interval, to some unknown point, you call it x, basically where x is any point, any value between a and b, up to including b, and the integral of some smaller function f. Okay, and here we're using instead of using a t here to integrate with, instead of x, we're not using x in two places. This is something called a dummy variable. Let's take a look at what we're talking about over here on the right side. Okay, so kind of a graph you've seen before. Here's a and here's b. Okay, so our function looks something like this. This is our f of x. All right, so we're starting here, and at some point in between a and b, could be anywhere, including b itself, we go to x and we integrate this area onto the curve between a and x, and that area is given by this area function. Okay, this integral, definite integral, so a to x of actually this is our f of t, technically our function f of t dt. Okay, so we're just integrate that, meaning we find this area under the curve from a to x, and that's what's called our area function. Okay, now once again, part one of the fundamental theorem of calculus says that if I take the derivative, that the area function and actually I realize I have a typo here, so what I need to put is actually the derivative. Let me come back on the left side. I realize I made a typo here. What I should say is this. Okay, if I take the derivative of this area function with respect to x, okay, and basically that's just going to be f of x. Okay, that's what part one of the fundamental theorem of calculus says. Okay, so the derivative with respect to x of a of x is f evaluated at x. And once again, so if we move x back and forth, of course, it changes the area under the graph, and that changes our function, essentially the amount of our area under the graph. We take the derivative of that, just gives us f of x. So that means that it says over here that f, I'm trying to make this little control thing go away, and it's annoying me. There we go. No, well, ignore it. No problem. Hang on a second. Fix this. There we go. Okay, just have to ignore it. Okay, so what it says, what this means is the area function is the antiderivative of the function f on this interval. Okay, so remember what an antiderivative means. is that basically the antiderivative is what you take the derivative of to get the function f. And that's what we see right here. Okay, that's part one. Now, I'm also not really going to prove this fundamental theorem of calculus here. So if you want a proof of this, how it actually works, you can look that up just look up the proof of this on the internet. You can find other videos, other information about that, just to show you how it works. Now, part two is the one we're actually going to use more often. You're going to see more often. And that is the one that actually shows you how to find the value of the antiderivative. So part two says this. If we have the same integral from have an integral from a to b, okay, function f of x dx. All right, and let's just do a little picture of that. So this is very much like the first picture. So this time we're going all the way from a to b. We're not stopping at x. A to b, this area here, okay. So what this is, the fundamental theorem of calculus says this is f of a f of b minus f of a. Okay, so we take the antiderivative and evaluate that at our endpoints, and that gives us that value of that integral. Okay, where f of x is an antiderivative, just abbreviate that, of f of x. And we're and because think back to the idea of an indefinite integral, they always had an antiderivative plus some constant c. So maybe wonder what happened to c. We think of basically, since we have definite bounds, that actually fixes specifically which graph we're talking about. So we actually kind of eliminate the c that way. Okay, so this is the most important then version of the fundamental theorem of calculus. This is one we're going to use the most. Okay, this tells us, and this actually connects derivatives. This fundamental theorem of calculus, both parts, is what connects derivatives to integrals. Okay, so basically, if we have a function, some function like a, and we integrate its derivative from a to x, then we get that function, okay? Or if we have the integral of some function d of x on some f of x, then from a to b, then we can actually find the integral, find the area of that curve by finding the antiderivative, evaluating it at the endpoints. Okay, so with seeing that, let's practice with this. So let's also review a couple more things where we actually take a look at some examples. Okay, so you've probably seen these before, either some of my videos or other places. The one we're going to use a lot, of course, power rule for indefinite integrals. Remember what that said. So you have a power. So this is like a polynomial. X is some power p. Of course, give any power. P just can't be -1. Then basically, this is how we integrate it. And this is all. Remember, this is an indefinite integral. So we have the c here. Okay. We don't use, but if we have a definite integral with bounds, we don't use the c. And basically, so what we do is that we add 1 to the power, then divide by the new power. And we also have some common rules of integrals here. And the main ones we're going to use to help us with this are number 3 and number 4. Okay, so 3, if we have a sum or difference, and these are rules that basically mirror what we see with derivatives. If we have the integral, definite integral, or actually indefinite integral either, of a sum or difference of functions, we can break them up like this, still using plus or minus, whatever's in between. We have a constant in front, and on the inside, we pull the constant out. Okay, and those are basically the same rules for derivatives. So let's look at some examples and practice with this. And I'll just start a new page. Let's say I want to find, or instead of saying find, you can say find, let's also say evaluate. A definite integral. Okay. So let's start off with some basic ones to begin with. All right, so number 1. So let's just start with a very basic one to start with. Let's say we integrate just x dx from, say, 1 to 3. All right, let's make it 2 to 4. Okay. Now, look back at our fundamental theorem of calculus. Okay, well, it's mainly going to use the second version, part 2. What the rule says is that this is going to be equal to its antiderivative of x evaluated at 4, the upper bound first, minus the antiderivative evaluated at the lower bound. So let's find the antiderivative, okay? So f of x, remember we have x, then using the power rule we just mentioned, okay, that's going to be, so the pair of the power of x is 1, so we add 1 to the power, which is 2, then we divide by the new power, okay? That's the antiderivative, or an antiderivative, all right? And so this integral from 2 to 4 of x dx, and also introduce a notation, is going to be x squared over 2, and this is also some notation we use sometimes write a straight line to indicate now we're going to evaluate it at our endpoints. Okay, so this evaluate the endpoints, and so the next thing we just plug that in, and so we have 4 squared over 2 minus upper value, then 2 squared over 2 minus the lower value. That's the reason I picked 2 and 4 to have something that will cancel out. Of course, 4 squared is 16 over 2 minus 2 squared is 4 over 2. And so that's going to be 8 minus 2, or it's going to be 6. Okay. And also, if you always do like a quick picture of this, so this is just this line, y equals x, from 2 to 4, just going to look like this. If the line looks like that, and we're just evaluating that. So actually, let's go to, real quickly, go to Desmos and graph this. Y equals x. Okay, so from 2 to 4, essentially what we have is like, and you can actually check this out on your own. So what we have is a square right here and a triangle, and you can actually check that. In fact, we can actually do it right here. So if you notice, the square is 2 units long, 2 units high. So the area of that is 4. And then basically we have half that square here. This triangle is half that square, which is another 2, which is 6. So it's exactly correct. Okay, so actually I can do these by hand without having to calculate the areas using Riemann sum or some other method. Okay, number 2. All right, so this time let's actually do one where we're combining some of these ideas. So let's say we go this interval from -3 to 1 of x squared plus 2x dx. Okay, let's go to Desmos then and graph this. Let's turn that one off. This time y equals x squared plus 2x. Okay, and I want to go from -3 to 1. Okay, so right here is negative, we're -3. So -3 and 3. Let's just highlight that point. So -3 and 3, label it. And to 1. So when it's 1, 1 and 3. Okay, 1 and 3. So that's what we want to do. Now, also one thing to notice here is that part of this area is below the axis. Remember, so any area we have above the x-axis is considered positive. Any area we have below is considered negative. Okay, so if we graph this, so a little basic graph. So here is -3, 3, and here is 1, 3. So this graph looks like kind of like this. So the area under the graph is going to be right here, and also right here. Okay. Imagine, especially that's going to, if we try to do it some other way, we've tried to use geometry, it would be hard to do because these aren't going to be nice geometric figures like triangles or squares. Okay. Of course, you use Riemann sums, but we don't have to. This gives us an exact value. All right. So we're going to do then, let's take a look at our rules and use this. So first off, let's break this up into two. And so this is going to be the integral from -3 to 1 of, right, this is x squared dx. I put the dx as each one. Remember, the dx is a differential that comes from, for a definite integral, the limit of the Riemann sum of your width of your rectangle essentially going to 0, becoming essentially d of x, and then plus integral from -3 to 1 times 2 times x dx. Okay, I put the dx as each one like it shows here. All right, now one more thing we can do here, we can also pull this constant out front. Okay, so we have -3 to 1 of x squared dx plus, and we make this 2, then the integral of -3 to 1 x dx. Okay, so this is the same thing. So using those rules, this is going to give us the same value. Okay, now let's actually find the antiderivatives. Okay, and so we have two separate integrals. So the first one, all right, so how do we integrate that? Well, let's use our power rule again. So power is 2, so we add 1 to that is going to be x cubed. And then do we divide by the new power, which is 3, and then we put this little line here. And so we're going to evaluate that from -3 to 1, plus, and here we just did this a minute ago, the antiderivative of x squared, or x is x squared over 2. And then once again, the same way, evaluating that from -3 to 1. Okay, so once again, here, for each one, we use the fundamental theorem of calculus. Okay, and so this is going to be x cubed over 3. Sorry, it's first going to be, use our upper bound first, which is 1. Okay, replace the x with 1, minus, replace the x with -3. And we'll take care of all that here in a minute. Okay, now plus, then do the same thing over here. Replace the x with 1, so 1 squared over 2, minus, and then replace the x with -3 squared over 2. I have to work the fractions a bit, but that's okay. All right, so simplify everything. So that's going to be 1/3. Here, if you notice, we're subtracting. It's going to be minus. This is also going to be a negative. -3 squared is -27 over 3, which will reduce, which is nice. This, of course, will be 1/2. And this is going to be minus. And if we square negative, we get a positive. So -9/2. Okay, so let's keep simplifying. 1/3. This is actually plus. In fact, I may just, let's see. Now I'll go ahead and turn this into 9. I'm trying to think, my better leave is a 3. Then plus, and actually, let's go ahead and combine these. Okay, we can do that in order of operations as long as we make sure to use our signs. And so this is going to be 1/2 minus 9/2, and that's going to be -8/2, which will come out evenly. So that's good.
Are you coming back in?
Second. Okay. You notice anything? I had to pause it briefly. Okay. And so that, of course, is going to be 1/3 plus 9 minus 4. So that's going to be 1/3 plus 5. Okay. Then, of course, write 5, the denominator of 3. So multiply the top and bottom by 3. And so we have 1/3 plus 15 thirds. And so that's going to be 16 thirds. Okay. 16 thirds, or if you can approximate that, let's see, a calculator, if we do approximate that, 16 divided by 3 is about approximately 5.33 repeating. Okay, right. The main thing to take away is not the algebra so much. That's something you should be able to do. But once again, how we did this. So we started out with this expression, right, string mark. we broke it up, and using these rules we mentioned, we broke it up into two integrals, and also pulled the constant out. And so we had two rules. Use the power rule. Then you evaluate each one using the fundamental theorem of calculus, evaluate each one of the endpoints. Then we got our answer. Okay. Now, this also works once again, no matter how many things you have added or subtracted together, it works the same way. Okay. Let's see what's next. All right, let's take a look at our next example. All right, this time, let's do integral from 0 to pi over 4 of 2 times the cosine of x dx. Okay, so once again, let's graph this. I'm going to graph all of them. Let's graph a few of them. So first off, let's turn these off. Remember, we default in radian mode. Radian mode is what we want. So y equals 2 cosine x. Ooh. Oh, that's wrong. Okay. Now, going from 0 to pi over 4. So pi over 4 should be right here in the middle. Okay, if this is pi over 2, be right here in the middle. From 0 to pi over 4. Okay. So the graph of this should look something like what we just saw. There's 0, pi over 4. It should kind of slope down like that. And it's going to be coming, but right here is going to be our area. Okay. All right. So once again, let's do the same thing. Once again, like before, we can bring the constant out. And so this can be 2 times integral from 0 to pi over 4. Okay. And the cosine of x dx. Now, this doesn't involve the power rule. This is where you want to think about the integrals, the derivatives you learned so far, and think what function has a derivative of cosine of x? In other words, what's the antiderivative of cosine of x? Remember, that's sine. Okay. So also don't forget the 2. What? Crap, I apologize. I made a mistake. I just realized I made a mistake on the first one. You know what? I hate doing this, but I'm actually going to erase the, I'm going to get rid of the 2. It's either that or I have to work back through the entire thing. So what happens was I forgot the 2, which I always have to be careful. So the 2, I forgot the 2 out front. So we'll make sure we don't do that on this one. But I'm going to erase it here just because to avoid having to go back through and do all that. So let's pretend that 2 wasn't there. Okay. All right. So once again, I apologize for that. I wasn't being careful enough. I'll just always be careful. Okay, let's make sure we're more careful on this one. So don't forget the 2. It's easy to do as I just did on that one. Okay, so 2 times, the way I often do this when you have a number in front is kind of make a, this is kind of addition, there's nothing right or wrong about this, but a bracket. And so this is going to be the sine of x evaluated at pi over 4 and 0. Okay. So once again, don't forget the 2. The 2 is still there. So this is going to be 2, and then using the fundamental theorem of calculus, like we've been doing, what this says, and this is the antiderivative evaluated at pi over 4 and 0. Okay, so it's going to be the sine of pi over 4. And I might be good to just use brackets on this so I don't have too many parentheses. Okay, then minus the sine of 0. Okay, now remember the sine of 0 is actually just 0. Okay, and then the sine of pi over 4, remember that one is that's the same as a 45-degree angle, and that's the same as the square root of 2 over 2. The square root of 2 over 2, okay, minus 0, or 2 times the square root of 2 over 2. Of course, the 2's cancel out here and here. We're just left with the square root of 2, which is about 1.41. Check in your own calculator. About 1.41. Okay. So that's our integral, definite integral right there. All right. Now let's take a look at a few other ones. And let me see which one I want to do next. Okay. So I'm going to start a new page again. So that was number 3. This is number 4. Okay. Now this time the integral from 1 to 2 of, and we have a fraction, so 2s squared minus 4 over s cubed ds. So this time I'm using a different variable instead of x, we're using s, which is fine. Okay. Now this time I'm not going to worry about graphing it and everything. It's probably a more complicated graph. But let's think about this. So once again, how can we simplify this? Because right now it'd be really hard to integrate this way. What we want to do is once again use the properties we mentioned. And so first off, let's kind of work with this in the middle. So the square root of 1 to 2. Now the best thing to do here is probably to break this up into 2 fractions. And so we have 2s squared over s cubed minus 4 over s cubed ds. Okay. And as you can see, we can rewrite the first one as that's going to be 2 over s minus 4 over s cubed ds. Okay, so now this should look familiar with what you've seen before. So let's actually break this up into 2 integrals. And sorry, 1 to 2, not 0 to 2. Okay, so the first one's integral from 1 to 2 of 2 over s. I'm trying to make sure my s's don't look like 5s times ds. Minus, this time we have a minus, that's important. Integral from 1 to 2 of 4 over s cubed ds. Okay, now let's do a couple more things. And notice this 2 here and this 4 here, those are constants. I can bring those out front. Let's do that. So 2 out front, and then 1, 2 from 1 over s ds. I'm going to do a couple of things here. I'm going to bring the 4 out front, but also I'm going to write this is the same thing as s over 1 over s cubed. I'm going to write that as s to the negative third ds. And that's going to make it a little bit easier to work with. Okay, so let's go back over. Remember our power rule. Now, if you notice, just remember a couple of things. This one doesn't fit the power rule. Remember, we said as long as, actually, let's do one more step. 1 over s cubed. And this is the same thing as 2, integral from 1 to 2, and I'll write this as s to negative 1. You don't have to, but make sure it's clear. And this one, once again, is s to the negative 3 ds. Now, let's think about the power rule. If you notice this time, I can't actually use the power rule here. This one says when your power is not equal to negative 1, and it is. Now, hopefully, thinking back on your derivatives, you learned what has a derivative of 1 over s? That's actually the natural log function. So this first one is going to be 2 times the natural log of s evaluated at from 1 to 2. Okay, that's the first part. Now, minus 4. Once again, don't forget our constants, 2 and 4. This one, we can use the power rule. Okay, we use for any power just as long as the power is not equal to negative 1. And so remember how this works is we add 1 to our power, so negative 3 plus 1 is going to be negative 2 over the new power, which is negative 2. And then that's evaluated from 1 to 2. Okay, so here, basically, the calculus is more or less done. We just have to plug in a few things. All right, so here, let's write this as 2. So this can be the natural log of 2. The fundamental theorem of calculus evaluate the first endpoint minus the natural log of 1. Okay. Now, hope you remember the natural log of 1, any log of 1 is 0. Okay, that makes it simpler. Here, minus 4. Now, this one's probably going to be easier to write this. Actually, let's do a couple things first. it's probably easier to write our power. Let's actually take care of that first as 1 over s squared. It's probably less awkward that way. Let's think about our constant. We have a -4 out front, but now we have a -2. That's also a constant. So -4 times -4 divided by -2 is going to be +2. Okay. Let's remember, if it's been negative, you have to distribute a 2. All right. So here we have 2 times the natural log of 2. All right. That goes away. Plus, over here, 2 times 1 over 2 squared, the first endpoint, minus 1 over 1 squared, the second endpoint. And we're almost out of space. I'm just going to combine this into 1. So 2 times the natural log of 2 plus 2 times 1/4 minus 1, is 1 over 1 squared is 1. And so 1/4 minus 1 is -3/4. So we're almost there. So 2 times the natural log of 2 plus 2 times -3/4. 1/4 minus 1 is -3/4. And finally, we get our answer 2 times the natural log of 2 plus, divide the 2 more by 2. So that's going to be negative, or actually minus 3/2. Okay, that's the exact answer. Now, that's not all that useful. So one thing you can do with your graphing calculator, scientific calculator, also with Desmos, let's actually simplify that. The 2, remember, the natural log of 2 itself is just a constant. So let's actually find out what that is. 2 times the natural log of 2 minus 3/2, and that's approximately negative, let's do 2 places, negative 0.12, or second, negative 0.11. So that's approximately negative 0.11. Okay. Yeah, so if you have a fraction like this, the best thing is to break it up into more than one fraction and then do the same rules. Okay. Let's see what's next. That was number 4. Number 5. Okay. Number 5. Let's say we have something like this. The integral from 0 to 4 of t times t minus 2 times t minus 4 dt. And also, whatever variable you have on the inside with this t should have the same d of that. So this is, shouldn't have like a variables involving t, even like a d of x or something like that. It should always be the same variable. Okay. Now, the best thing to do in case like this, there's no really good way to integrate this as it is. What we need to do then is just basically multiply this out. Okay, there's really no good way to do it besides that. I think the first thing I'm going to do is I'm going to just FOIL these two. So I have t in front. Of course, remember, t is a variable. We can't pull the t out front. It's not a constant. So let's FOIL these. So that's going to be t squared. Okay. And then I'm actually going to do a couple steps in one. So just make sure you follow me on this. So the outer term is going to be negative 4t. The inner term is going to be negative 2t. So to combine those, it's going to be negative 6t. And then finally, negative 2 times negative 4 is plus 8 dt. And then finally distribute the t through. And so we have the integral from 0 to 4 of t cubed minus 6t squared plus 8t dt. Make sure we put parentheses around that. Okay. Now we have something more normal, the kind of thing we've seen before. It's nothing different. We just have more to do because we have 3 parts. We have 3 different integrals, but everything's working exactly the same as we've already seen. Okay, so let's break this up into 3 integrals. So from 0 to 4, t cubed dt, don't forget the dt's, minus the integral from 0 to 4. Also have the same bounds and everything, from 6t squared dt, okay, plus, since we have a plus right here, 8, an integral from 0 to 4, 8t dt. Okay, and then once again, we can pull the constants out front. So I'm going to leave this one as it is for right now, 0 to 4 t cubed dt minus, bring the constant up front, minus 6. And inside we have the integral from 0 to 4 t squared dt. Then plus, pull the 8 out front, and then the integral from 0 to 4 t dt. Okay. Now this last one we've already done before. Okay, that's the same as the integral from x dx. Okay, just using t as a variable instead. So once again, use the power rule. And so this is going to be t cubed. It's going to be t to the 4th over 4, evaluated from 0 to 4. So make sure that it doesn't look like it's like a 6. Maybe 0 is going to make our life a lot easier. Okay. Minus 6. And then the same way, the integral of this is increase the power by 1 t cubed over the new power, which is 3, evaluated and from 0 to 4. And then finally, plus 8 times, it's going to be t squared over 2 from 0 to 4. Okay, and now just use the fundamental theorem of calculus, plug in our bounds. So the first one is going to be 4 to the 4th divided by 4 minus 0 to the 4th divided by 4. Of course, that part's going to be 0. Minus 6. The only thing you want to be careful about here is subtracting this whole thing. So this simplification, I have to distribute the negative. Okay, so 4 cubed over 3 minus 0 cubed over 3. Of course, that's going to be 0. And then plus 8 times, evaluate the bounds, 4 squared over 2 minus 0 squared over 2. And once again, this last one's going to be 0. It's going to make life a lot easier. And so put all that together. 4 to the 4th, if you don't remember that, 4 to the 4th is, I remember that. 4 to the, that's 128, I think. No, 250. All right, 256. Oh, it's 256. Okay. So 256, 4 to the 4th over 4. Take care of that in a minute. Okay. Minus, never get this 6 times 4 cubed. And I guess 4 cubed is 128. 64. Yeah. 4 over 3. Okay. And plus 8 times 4 squared, of course, is 16 over 2. Yeah. So this is still going to go pretty nicely. All right. So 256 divided by 4 is actually 64. Okay. Now this, we can think of 3 going into 6 twice. So 2 times 64 is minus 128. And then finally here, and think of this as 2 going into 8 4 times. So 4 times 16 is also 64. This is interesting. Notice what's going to happen. It should be 0. Let's see if that makes sense. So actually, let's graph this one. Okay, so let's graph it the way it was written. We actually got a 0. So that means we should have the same area above and below. Now, it may not look that way. Let's see what this looks like. So y equals t times t, oh, we choose x minus 2 for graphing purposes, times x minus 4. Okay, yeah, and that's actually perfectly reasonable. If you look at this graph, okay, from 0 to 4, right. So we have this part, and these parts looks like they're pretty much the same. This area here, essentially, is positive. This is negative. They cancel each other out. The integral is actually then 0. Okay, which that makes sense. That happens sometimes. What that means as far as meaning an integral, like an accumulation of the sum of something, is you have like equal parts positive, negative, canceling each other out. So when you think once again, think of the idea of filling up a bucket with water. Maybe the first part of the graph is filling it up at a certain rate. The water's coming at a certain rate. And then maybe you open up a hole in it and it drains out at the same rate. And then over this amount of time, then basically the change is essentially 0. Whatever you filled up to begin with in this part was drained out in kind of the same amount of time and the same rate as this was. And so you're left with nothing. Okay, let's do 1 or 2 more. And I think this will be number 6. I think hopefully everyone's getting the idea of how this works. All right, let's do one more you might have to think about just a bit. Well, let's see if we want to do that. Hang on, so we want to do that or not, maybe something else. Okay, let's do this one. Let's say we have this from 0 to pi of and I'll just make it 0 to 1. Make it simple. 0 to 1 of 1 over 1 plus x squared dx. Okay. So what you want to do anytime you see these, especially something a little different, is start thinking about the derivatives you've seen, and we're thinking about going backwards. Okay. So this is one you may have done too many times. And hopefully, if you remember what this is actually this is one of your anti or inverse trigonomic function derivatives here. Okay. And so we do that then. And so this is going to be, this is actually inverse tangent. So this is actually equal to the inverse tangent of x evaluated at 0 and 1. Okay. Now, let's do that then. And so the first one is going to be the inverse tangent of 1, using the fundamental theorem of calculus, minus the inverse tangent of 0. Let's actually use Desmos to help us out with that. Remember, we're essentially in radian mode for the inverse tangent. Go down here. Now, I believe a couple ways to do inverse tangent. One way is, I believe, to look at our functions. We actually have it right. So inverse trig functions right here. Let's do tangent of 1. Okay, here we just use decimals. That's fine. So about point for 1 is about point, let's just do 2 places for simplicity, 0.79. Approximately, this is 0.79 minus. Now, the other way you can do an inverse tangent is, you may have heard sometimes inverse trig functions are called arc, like arc tangent, arc sine, arc cosine. You may have heard that. We do that, so arc, or I'll just do the same thing, tangent of 1 to make sure you get the same thing. We do. Okay, let's do arc tangent of 0. That is just 0. Okay, that's nice. And so our final answer then is approximately 0.79. Okay, and that's our result. All right, so let's review what we learned so far. So we learned the fundamental theorem of calculus. This is how it finally shows how we connect integrals and derivatives. And we primarily use this result most of the time, although this is important. But this you probably use this part 2. What it says, remember, is that we have a definite integral from a to b on some function f. Then the definite integral, the area of that curve, is given by evaluate the antiderivative at the right endpoint b, the bigger endpoint, minus the antiderivative evaluated at the smaller endpoint. Okay. Then we also reviewed some of the things we need to help us find these antiderivatives, which are the power rule, which you can't use any power except for -1. That involves a logarithm. And also some of the properties of integrals, especially properties 3 and 4, which once again very much like, or essentially the same as the same properties for derivatives. And that allows us to take a more complicated integral and break it up into smaller ones to evaluate the parts. And then, of course, just the algebra, then actually getting the final result. Thank you. Have a good day.